Again, this is software that's highly tuned to optimize all the benefits of the Pentium 3 and running at a full 600 megahertz on the Pentium side, still 2 to 1 slower than the 500 megahertz PowerPC G4 chip and Power Mac G4 system. All right, Pentium's done. Now, these 3 demos that Phil and I have just showed you, we hope are of particular relevance to you being in the design and publishing space, whether you're creating printed materials, electronic materials, obviously for the internet, etc. But we also serve a lot of other customers in science and in education. And I've asked one of Apple's distinguished scientists, Dr. Richard Crandall, to come up on stage and give us a few demos that relate to some of these fields that we've been working on. And I'd like to introduce him right now, Dr. Richard Crandall.
Greetings. As a career scientist and teacher, I am ecstatic about this desktop supercomputing with G4. Over the years, I have been privileged to use, I think like some of you here, from time to time, supercomputing, usually through giant supercomputer centers or government centers. And even so, even though we got to use some supercomputing, it was problematic, it was ad hoc, and it was always too expensive. There was a time when we had to pay $1,000 for a CPU hour to get this kind of speed. However, with G4, things are going to change now. And, for example, back at my laboratory, as I speak to you, I have a brace of G4s doing a very tough calculation, one of the toughest around. And because of G4, this will finish by Halloween. If I had been using the old dinosaur supercomputers, then even during this little talk to you, I would be going bankrupt. Boy, do we have some supercomputing examples for you. We have 3. You will see, for example, before your very eyes what a gigaflop looks like in an example. Let's start with SETI at home, which means Search for Extraterrestrial Intelligence at Home, meaning that from this Berkeley site, SETI at Home, a Berkeley research group, you download code that contains signals from outer space, data that contains signals from outer space and code to process that. On the right, you see a Pentium 3 processing this data, which is centered at 1420 megahertz, a special cosmic frequency that we think a remote civilization would use. That looks random, that spectrograph, because, well, if you see a pattern in that, that's a big deal. So the SETI at Home people actually did a brilliant thing. They have had over 1 million downloads in over 200 countries, so that there's this worldwide volunteer giant supercomputer. And so the natural question is, how would this perform on a G4? So on the left, you see the same kind of calculation on the same kind of data set on G4. And you can see it's obviously running faster in some qualitative sense. But in reality, it takes 6 hours to data process on the G4, what takes 25 hours on the Pentium. That's more than 4 times faster. I want to say that at the core of the SETI at Home software I'm showing you is an FFT, or fast Fourier transform, that's important in many fields, as you know, I think, which runs at supercomputer speeds. And because of that core routine that's really blazing, the whole application is 4 times faster. Now, you've heard of the Andromeda Galaxy, and you've heard of the Milky Way galaxy, our galaxy. Let me introduce you to the G3 galaxy. Wow, that's very respectable. That's 30,000 stars. And I need to make this point, it's important, that this is not just animation. This is calculating in real time. It's solving physics equations in a certain gravitational model. Every star is moved around according to the laws of Newton and using the gravitational constant and so on. And that's very respectable. If you do 2,000 stars, it swirls really smoothly on a G3, and that's a lot of power. But this 30,000 stars kind of brings the G3 to a certain kind of a staggering mode. Now I'll show you 1 billion operations per second on the left. There you go. That is one way to look at 1 billion operations. Here's another interesting way. At a gigaflop, in the time it takes to do one operation, light travels 1 foot. So this means, and light is, one way to think of how fast light is, it goes around the Earth 7 times a second if you guide it around. It goes around the equator 7 times a second. So this means that when you're running your desktop supercomputer, during one operation, the light that leaves the monitor screen has not reached your face.
Okay.
Again, to compare G3 and G4, we have a demonstration of cryptography. Now, many of you know, in fact, I think everyone knows, that in modern cryptography, large numbers are the key. And that the mysteries of the way large numbers work are, lie at the core of modern cryptography. And so it's getting harder and harder to do the computations necessary for security, because we've all heard, like just a week ago, another break of another encryption system that was, maybe 150 bits, and you can break 200-bit systems. And now we need to do 1,000-bit keys, and later we'll have to do 5,000-bit keys. But this is a 1,000-bit key, which has encrypted 2 images. The right-hand image is the G3 image, and the left-hand image is the G4 image. And of course, G4 will pick up 128-bit chunks of the key and process that with its natural speed up. Let's race these.
3, 2, 1, go.